Welcome back to our class. Now let's continue our discussion for the key technical challenge to the optical communication in the next decade. In this chapter, we will discuss the development trends and challenges for the key technologies in the optical communication field in the next decade. Before we discuss the specific technology trends and challenges, let's look at the innovation curve in optical communication first. The innovation of optical communication technology, which is similar to the innovation of other fields, it actually follows the rules that the theoretical breakthroughs come before the application innovation. For example, technological innovation can create a new laser technology, and application innovation can develop an optical communication product with higher bandwidth or longer distance based on the new laser technology, and then replicate it on a large scale. Currently, there are many theoretical breakthroughs in the field of basic research related to optical communication, such as quantum communication, hollow core optical fiber, and optical storage. Next, the industry needs to continue technological innovations based on this series, find application scenarios, and replicate these technologies to optical communication network applications. While some of these application innovations, such as 10G PON, 200G, and 120 wavelengths technologies, have been implemented on the live network already. In the next decade, new technologies and applications in the field of optical communication will be based on these basic theoretical breakthroughs and try to solve the problems we encounter in the development of optical communication. Here are our list of 9 technology trends and challenges. The first trend is ultra-high speed, that is, high bandwidth. With the 5G densification deployment and the emergence of new services, which will bring higher bandwidth requirements for the optical communication on the backbone networks. Secondly, it is the ultra-broadband spectrum. Expanding the available optical spectrum is one of the important directions for providing large network bandwidth. The third trend is to use new optical fibers to meet the requirements for ultra-long haul and ultra-high bandwidth transmission. The fourth is non-linearity challenge. As the single wavelength capacity increases, a new algorithm needs to be found to reduce the impact of non-linearity on system performance. Fifthly, optical network needs to be digitalized and intelligent to improve the resource efficiency and operation maintenance efficiency. Number 6, optical layer grooming needs to reduce the loss and improve the cross-connection dimensions to meet the requirements for ultra-large capacity grooming for single node in the optical layer. Building an optical access network architecture to achieve high bandwidth is the 7th development trend. In addition, we also need to seek some breakthroughs in inter-satellite optical communication and optoelectronic module integration. In this chapter, we'll discuss the first challenge. Can the single fiber capacity of a long-haul optical system exceed 100 terabits per second? So here are a few sets of figures based on our recent insight and forecast on carriers optical networks. In the coming years, long-haul optical networks will maintain a capacity growth rate of 25% to meet the requirements of the new services like 5G, cloud VR, 4K video, and data center traffic growth. Based on this logic, long-haul optical network bandwidth will double within 3 to 5 years. It is estimated that by 2030, we can reach single fiber capacity of 100 terabits per second. The bandwidth has changed from 10 years ago, 80 wavelength 100 gig system providing 8 terabits capacity per fiber to an 80 wavelength 200 gig system where the single fiber 16 terabit solution has become the mainstream. In year 2020, single wavelength 800 gig solution, which can provide 48 terabit per second capacity by single fiber solution, has been put into trial commercial use by some operators around the world already. The next generation backbone WDM network will evolve to a single fiber 100 terabit capacity system. Here, you may have a question. Can we infinitely increase the capacity of the WDM network? Before we reveal the answer, let me show you how to increase the capacity of a WDM system first. There are several methods to improve the single fiber capacity of a WDM system. Increasing the rate of single wavelength is one of them. Another method to increase the overall capacity of a single fiber, it is to improve the spectral efficiency, which is short as SE. SE has changed from 2 in the 100 gig single wavelength era to 2.67 in the 200 gig era. Right now, it has been a great challenge to achieve full spectral efficiency in the 800 gig and 1.6 terabit era. Here, you must wonder what spectral efficiency is and how to improve it. Spectral efficiency refers to the number of bits that can be transmitted per second on a transmission channel per bandwidth unit, in bits per second per hertz. In telecommunication network, increasing the modulation order is usually used to improve spectral efficiency. For example, a 100 gig single wavelength uses the QPSK modulation mode, and one symbol may carry 2 bits. In the 200 gig single wavelength solution, the 16 QAM modulation mode is used, and one symbol can carry 4 bits. In this case, the system bandwidth can be doubled compared with that of the 100 gig single wavelength solution. In the future, higher modulation orders like 64 QAM will be the main means to improve the capacity of WDM networks. The second approach is to expand the spectrum of optical communication to accommodate more channels. Currently, the most common WDM system use C-band and 4 terahertz spectrum. This can provide 80 wavelengths. For a long-distance optical network, we also need to consider not to reduce the transmission distance when we increase the system capacity at the same time. So according to the Shannon's theorem, the higher the spectrum efficiency, that is, the higher the modulation order, the higher the signal-to-noise ratio requirement for the system. As we know, the signal-to-noise ratio of an optical communication system will decrease as the transmission distance increases. This will limit the transmission distance of a high modulation system. As a result, it is impossible to provide system capacity by increasing the modulation order unlimitedly in actual applications. This is the biggest limitation and challenge to improving the single fiber capacity for the long-haul optical systems. Lastly, let's have a brief summary. In this chapter, we discussed the innovation curve in the optical communication field, some basic theoretical research and innovation in the optical communication field, and the corresponding application innovations, such as 120 wavelengths and 200 gig. In the second part, we look forward to the development trends and challenges of the optical communication in the next decade. Finally, we introduce the evolution chain of single fiber capacity in long-haul optical systems from 3 aspects: the rate, spectrum, and span distance. That's what we have covered in this section. Next, let's have a small quiz. We will have 2 questions to consolidate the contents of this section. First, it is a single choice question. Which of the following is not included in the key technical challenges and chains of optical communication in the next decade? This is a single choice question. A. Ultra-high speed. B. Ultra-wide spectrum. C. New sites. D. Non-linearity. E. Optical network digitization and intelligentization. So we say that ultra-high speed, ultra-broadband, spectrum, non-linearity, digitalization, intelligent optical networks, they are the chains or challenges in the optical communication. Therefore, the answer is C, new sites. This is not one of the evolution chain or the technical challenges. The second question, it is a multi-choice question. Increasing the single wavelength rate or expanding the available spectrum can increase the single fiber capacity of a long-haul optical system. Which of the following statements are correct? A. Using higher order modulation scheme can increase the amount of information carried by a symbol. B. The higher the modulation scheme, the better. C. 800 gig single wavelengths can be carried by 75 GHz channel spacing. D. According to the Shannon curve, the higher the modulation scheme, the higher the OSNR requirement, and therefore the transmission distance is limited. So according to what I have introduced, we know that the modulation order limits the transmission distance. It's not the higher the modulation, the better. Currently, for the 800 gig single wavelength solution, we can only use 100 GHz channel spacing. So option A and D, they are correct. Well, that's all for this chapter. Thank you.